name's EJ. I'm from University of Delaware. And today I'm here to present my design for a flexible artificial muscle. So here's basically what it looks like. It's a cellular arrangement of individual actuators. First I'll show you the geometric approximation of the model, then the continuous deformable structure, and then we'll take a look at parameter optimization. So the inspiration for this design comes from the natural world. I wanted to replicate the properties of living creatures, their speed and precision of motion and flexibility, and I wanted to create that in a robotic system. So in order to do so, I took a look at the structure of biological muscle, which is cellular, and I decided to create an actuator that is cellular, which will allow it to have flexibility and multiple degrees of freedom. So each cell of the design is composed of a piezoelectric stack actuator, and I chose piezoelectric actuators because of their properties. They're fast, accurate, can apply a large block force, and they're mechanically simple. And these stack actuators are used in applications that require extreme speed and precision, such as space actuation. Here's a CubeSat, also in electron microscopes and sonar. So in order to create a muscle that's flexible and has many degrees of freedom, each cell needs to be manufactured at an incredibly small scale. And previous research has demonstrated the ability to do so. These are pictures of an amplified piezo actuator manufactured at the micron scale. So piezoelectric actuators are limited by their small output displacements, which is only 1/1000th of their original starting length. And commonly in industry, these actuators are used in conjunction with an amplification mechanism. So here's my design of the unit cell of the structure. It is a two-stage amplified piezo actuator. In this model, the geometric model, there's no losses. It's composed of rigid bodies with ideal pin joints, and it just serves as the upper limit for the performance of the design. So this is the unit cell. Here's an arrangement of 4 cells. And here's some results. We can arrive at a closed form solution for the performance of the geometrical model. Omega is the output strain rate, which is the percentage is the strain of the overall model, the multi-cell model. So omega is a function of some of the key parameters. And here it is plotted versus lambda, which is the ratio of the length scale of the first cell, the first stage to the second stage actuator, which you can see in that diagram. That would be L over L, little L over big L. And as you can see from the chart, the output strain can reach 0.5, which is a 50% contraction, which is a little unreasonable for certain values of lambda, but for more reasonable values of lambda, it can easily reach 0.1 or 0.2, which is a 20% contraction, which is on par with biological muscle. And this is up from 0.001 strain rate of the unaided piezo element. So just using geometry, we can also determine the output force based on the input force of each cell. And we find that there is a trade-off between amplification of strain and the output force. So this is going to have to be tailored for specific applications. However, you can increase the force by adding cells in parallel. So next we're looking at the combined mechanism. In physical systems, you can't have ideal pin joints, and especially at incredibly small scales. So in the industry, typically these amplification mechanisms for piezo actuators are composed of a single continuous deformable structure with small flexural hinges that bend instead of pin joints. So on the right is an image of an actuator used in industry. I mean on the left, and on the right is my design for a two-stage actuator that's a continuous deformable structure. And here's finite element mesh over the structure, and this is the true scale output. The actuation of the piezo, which is that rectangle to the left, the black rectangle, is not even visible, but the output is clearly visible. It's a huge amplification. And here's the multi-cell structure, this is based on assumed periodicity. So each cell isn't controlled individually, they're all actually the same. But it just shows how each cell would be combined to form this structure. So from the finite element, we have results that show that the compliant mechanism closely matches the predictions of the geometric model as the flexural hinges get smaller and smaller. So here it is plotted for multiple values. These are in millimeters for a 40 millimeter piezo. So the hinges are very small, and its performance is highly dependent on the width of the hinges. So we can also calculate the block force of the deformable structure, which matches closely with the geometric model. As you can see, most of the stress in the structure is within the hinges. So playing around with the finite element model, I was able to design 4 orientations of the unit cell, which each has unique properties. You can see alpha and gamma are contracting, while beta and delta are expanding with the actuation of the piezo element. And each one also has some other interesting properties, such as 2 of them have the greatest applicable force at the beginning of actuation, while others increase their applicable force throughout the actuation. And here's each of these in a multi-cell structure. So finally, we're looking at optimization. I use IMECE software, which computes stochastic variations across the parameters, the geometric parameters, and it converges to a solution that is much better than the starting solution. You see it's converging there. So this is a gradient-free optimization. And from the optimization, we have results that show on the left, omega converges to about 0.2. It's actually 0.18, which is 18% contraction. And it doesn't violate yield stress constraints. And beta configuration reaches 20% expansion. It also doesn't violate yield stress. The second 2 reach, on the left you see 50% expansion. However, this violates yield stress in the hinges due to bending. And same with the one on the right. It violates yield stress due to hinges, due to the bending stress in the hinges. So conclusions, in the future, I would like to take a look at the flexural hinges. There has been research that adds new materials or a material gradient within the structure, so that the links remain rigid while the hinges are flexible. And we're limited currently by the ability to manufacture at small scales. So in the future, I'd like to compute with each cell working individually to test its ability to produce motion in multiple degrees of freedom and I'd like to extend the structure to third dimension so that I can have degrees of freedom in all three dimensions. And I'd like to create a physical prototype. And in the end, I see this design having applications in robotics, prosthetics, sensing, and energy harvesting. Using the reverse piezoelectric effect, not only can you apply energy for an output motion, but you can apply a motion or a stretching or a force to create electrical signals and energy. And that's it.
We have 11 minutes. Yeah, we can get many questions. Yeah. Please go ahead. I'm sorry. Any questions or comment?
Let me start with that then. Thanks for your very interesting presentation. Based on your current work, what is your expectation of the actual limit of your, say, deflection displacement versus the amount of force that you can expect?
Versus the amount of force. So it will depend on the parameters. There's a trade-off between amplification and force. However, so it's almost proportionate. So if you amplify the strain by 100 factor, which is what this is doing to get up to 10% contraction, then you're minimizing the force by 100-fold. However, the piezo elements can produce a large block force, and you can also add cells in parallel. So you can really tailor the output force to a specific application.
Well, since you're considering the prototypes in future, probably you might guess some sort of the ranges that you can expect.
Yeah. Well, mostly I've been testing this in free actuation, to focusing on amplifying the strain. So afterwards, I'll focus on how much force I can apply with it.
Okay.